All right, so this is going to be our lesson on finding volumes of revolution for those shapes where you have something that's been revolved around an axis to make your three-dimensional shape. But finding those volumes is using a different method. This method for today is called the cylindrical shell method. So we're just going to start by reviewing cylinder. Say you have a cylinder. How would you find the surface area of this cylinder? So think about that. Now remember, if we unroll this cylinder, the circumference of the cylinder, this distance all the way around here, is going to be like this length here. And then the height of the cylinder is this length here. So we can just do that circumference times the height of the cylinder. That would be the area of this rectangle. That's also the surface area of our cylinder. Circumference times height gives us the surface area of a cylinder. Okay, so we're going to use that to figure out the volume of these shapes, because we can create these shapes using a whole bunch of cylinders inside of each other. So I'm just going to show you a quick video on what that kind of looks like. So this is a video that just kind of demonstrates what a cylindrical shell thing might look like. So this is a sphere, and it's just showing how you could create the sphere with cylindrical shells. So your top curve would be like a semicircle, and your bottom curve would be a semicircle, and then it would be rotated around the axis in the middle. And so it would just be all of these little cylindrical shells wrapped around each other, where as they go out and have bigger radii, they have shorter heights. So hopefully this helps you kind of visualize what cylindrical shells look like. Hopefully that kind of helps. I had a bunch of cylinders to show you this with, and they've disappeared from my cupboard. Somebody like stole them or something, so don't have those anymore. So hopefully that kind of helps you visualize what we're going to be doing. I'll keep trying to draw some pictures and things that might help with this as well. So let me turn on my document camera so you guys can see what I'm working on. Okay, so volume of a cylinder is 2 pi r, because that is the circumference, times the height. That's for area, surface area of a cylinder. Now if we want the volume, we times by thickness. So 2 pi r, that's the circumference, times the height, times the thickness. That gives us volume. Surface area times thickness is volume. 2 pi are just constants, so we can pull those outside of our integral when we're going to be adding a whole bunch of these infinitesimally thin cylinders together to get our entire volume. Okay, so again, r is the radius, h is the height of these cylindrical shells, that's what we call them, as cylindrical shells, and t is the thickness. So t is always going to be dx or dy, depending on what direction we do these. So if we're doing it in the x direction, the radius is just x, as long as we're rotating around the y-axis. The radius is always y if we're rotating around the x-axis. If we switch where our axis is, those are going to change just a little bit. The height is going to be f of x or f of y, depending on what we're rotating around. Now, if we're going around something different, then these y's and x's that are standing for the radius change a little bit. If the area is bounded by the curve and an axis, we just have the one function. If the area is bounded by two curves, we have outside curve subtract inside curve, which helps us figure out that area for the height of our cylinder. Okay? When the curve is not revolved around an axis, it says then just use the generic formula, saying come back, just use this, figure out the radius, figure out the height, figure those out on your own based on the information that you have. You don't really need to worry about these formulas. And you can always come back to this, even if it does fit one of these special cases. I always just come back to this, look at my situation, and fill this in. Okay? So again, if our radius is x, the height's f of x, the thickness is dx, If our radius is something with y, then our height's f of y, thickness is dy, and we'll draw some pictures to help you kind of visualize that and see that here in just a minute. The last little thing I want to talk about is this thing that it says to discuss here. Why would we want more than one method? It just depends. Some people really like the discs and washers method. Some people really like the cylindrical shells method. I like using both. I like using whichever one's going to make everything x and dx, so I don't have to worry about ever trying to switch everything over to y and change up my equations and all of that, for the most part. So that's what this is talking about. Most people tend to do that. So when we're rotating around a vertical axis, they use cylindrical shells, because cylindrical shells always is like the opposite of the discs and washers, whether you're using x or y. Also use the disc method when we're revolving around a horizontal axis. So shell method for vertical axis, disc method for horizontal axis. And so let's just try some examples and see what happens, okay? So here's our first area that we're going to be revolving, y equals x and y equals x squared. So let's just draw what that looks like. Y equals x, pretend that's a straight line, looks something like this. And y equals x squared looks something like this. So the area bounded by those is just this little sliver right here. So I'm going to just draw just like kind of a zoom in on that little piece. It's really bad, but pretend that's a part of my parabola. That's my straight line, y equals x. That's my shape. And to start with, let's just revolve this thing around the x-axis. That's like not even as big as the other one. Sort of there. That's maybe a little bit better. So we're revolving this around here. So we've got this three-dimensional shape that looks something kind of like this. It's got this funnel-looking shape taken out of the middle. The outside looks kind of like a top, maybe. This is our three-dimensional shape. And we're going to, instead of separating it into a bunch of discs or washers this way, we're going to separate this into a bunch of cylinders. So I'm just going to try and draw what one of those cylinders might look like. Maybe something kind of like that. Inside, kind of building this shape, right? So I've got a cylinder there, another cylinder like right here. Just a bunch of cylinders stacked, kind of partly inside of each other, partly not, to construct this three-dimensional shape, okay? So, for our integral, for finding the volume, we're going to be adding up all of these cylinders together. Okay, so formula again for volume of a cylinder is 2 pi, and since that's a constant, I can bring that out of my integral. And then I'm going to need a radius, and I'm going to need a height, and I'm going to need a thickness. Now you can see that since these are going around an x-axis, this is going to be one of our dy type situations. The thickness of each of these shells, this is kind of representing our thickness right here, is a little tiny sliver of y. So the thickness is dy. Now we need to find our radius. The radius changes for every one of these cylinders. The radius for this cylinder is from here to here. The radius for this cylinder is from here out to here. So it changes for each of these. But it's just a different y value every time. Since I'm rotating directly around this axis, there's a radius, but it corresponds perfectly with the y value. So the radius on this one is just y. Point that out. Y is the radius, dy is the thickness. And so we've got 2 pi RH. Inside these parentheses, I'm going to have the height. And then that would be our surface area, 2 pi RH. And then the thickness makes it become a volume. And then we're adding all these together. So the height of these cylinders is this direction. I'm going from this curve to this curve. That's where the height comes in. Between the two curves is the height of my cylinder. It's like my cylinders. They look more like cylinders this way, maybe of what you're used to seeing as a cylinder. So the height is this direction. The height's in between our two curves. Okay. So our outside curve was y equals x, but we now are going to switch that to x equals y. So just y. And, oh, that's not our outside curve, though. That's okay. I can fix that in a second. That's our inside curve, because we're going back to the y-axis. So our outside one's actually this y equals the square root of x. Let's solve that. Or y equals x squared, sorry. Square root both sides, so square root of y equals x. So that's our farthest away from our y-axis curve. When we're finding this height, it's from the axis to the outside, from the axis to the bottom. So this outside one first, inside one second, to this axis here. So square root of y is farthest away, and then just at y equals x, which is x equals y, is our inside one. So farthest away from the y-axis minus closest to the y-axis. And so that's just our setup. Volume is 2 pi integral y, square root of y minus y dy. The last thing we need is we do need our limits of integration. We want to know, in the y direction, everything here is y, how far am I going for this radius? This radius, the smallest radius right here, is 0, y equals 0, up to our biggest radius, right here at the very tip. What's that y value? Right there. Well, these just happen to cross at 1, 1, when x is 1 and y is 1. So we're adding up a little tiny, like not even any height cylinder here, up to this tall, super short one up here as well. We've got some longer ones in between that are getting wider and wider each time. So that would be the integral that we would use to solve this. I'm not even going to bother actually solving these. I know you guys have tools where you can solve those yourselves. Also do a little practice. Make sure you practice solving these without computers, and also you can practice letting the computer solve them once you're feeling comfortable with those, just so that we can hopefully make this video not quite so long as the last one. Just going to leave it at the setup, and then knowing how to do the integrals is old stuff that you guys already know how to do, so we're not going to go through that on this one. So let's take that same area and that same little piece of shape right here, y equals x and y equals x squared, that area between those two curves, and this time let's revolve, instead of revolving around the x-axis, let's revolve around the y-axis. So if we revolve this around the y-axis, we have something that looks kind of like this. This kind of rotated around shape like this. And if we're going to break this into a bunch of cylinders, I'm just going to draw one. I always just try and kind of draw one cylinder. I just go between the two curves on one side, straight across between the same two curves. You kind of get the idea of what one of my cylinders, or my cylindrical shells, might look like. Okay. So just looking at this shell, we can see that the thickness here is in this direction. The thickness is dx. The height of this particular one would be this length from here to here. That's the height. From this curve down to this curve. That's the height. And then the radius is coming from the axis that we're rotating around out to our shell. So let's actually write our equation from that. So 2 pi, let's look at that radius. That radius is going to start here at 0. That's what we're rotating around. And it's going to go out until the very edge of our shape in the x direction, which is 1. And the radius is just every x from 0 to 1. So it's just x. That's our radius. Then the next thing we're going to do is find the height. The height is going from this curve to this curve. From the x-axis up to our top curve, which is actually our straight line, which is y equals x. And then subtracting this piece right below that, which is from the x-axis up to this curve, which is x squared. So x minus x squared. That would be our height. And then we were in the x direction, so our thickness is dx. So that would be the volume. The formula for finding the volume with all of the pieces filled in. So then you could do that integral, that definite integral, and find the actual volume of this shape using the cylindrical shells. Like I said earlier, I like to do ones like this using discs and washers so everything's in dx. I don't have to do this work to switch everything into y's. And then I like to do ones like this in cylindrical shells so I can also just keep everything in x. I like things better when it's just x. Maybe you like things better when it's y. Maybe you'll feel more comfortable just with discs and washers all the time. Maybe you'll feel more comfortable with cylindrical shells all the time. But I do want you, when the book tells you to practice using cylindrical shells, practice it enough that you can get used to it. If you're feeling good about washers and discs, don't just always use those, because maybe you'll turn out that you'll actually like this one even better, or you'll like to do a combination. Okay? All right, now let's try rotating around something that's not the x or y axis. So we're going to, again, use that same shape. This time let's rotate around x equals 3. So that's x equals 1. I have to go quite a ways over here. If that's 1, that's 2, that's 3. I'm going to rotate around that. So we have to go 3 more over. I'm going to have something kind of like this over here. Okay, this is like way bigger than that. Just pretend they're like the same size. Okay, so we're rotating all around. That has a huge hole in the middle and just like a volcano shaped looking thing around the outside edge. So that is what our shape looks like. Now I'm going to try and draw one of our little cylinders in here. Hopefully I can make it look okay. So there's my super short, super wide cylinder that I'm making up my shape with it. And there's more cylinders, right? There's infinitely many infinitesimally small cylinders in here. I've got little tiny short ones that are out here, up here. My taller ones, which aren't very tall at all, are right in here. All these cylinders making up this shape. So the volume on this thing, using cylindrical shells, 2 pi. Again, I'm just going, or my radius is from my axis out. My radius on this particular shell is all the way across here. From there to there. That's my radius. So my radius this time isn't just x, because I'm not rotating around the axis. X would be the distance from the axis out to where I'm going here. I don't want that. I want everything but that. Between here and here, I want everything but x. So we're looking at this whole distance. It's 1, 2, 3. And then I'm going to subtract away the x that I don't want. So this is going to be 3 minus x for my radius. Just like before, I still want x to go from 0 to 1. I only want x's from here to here. For right here, I'm going to do 3 minus 0. Have the full radius of 3. And then my radius gets smaller and smaller up till this point where my radius is 2. It's 3 take away 1. So from 0 to 1 gives me all those radii from 3 when I plug in the 0, and then down to 2 when I plug in the 1. So 3 minus x is the radius. Now I want the height of my cylinders. My height on my cylinders on this one is going to be the exact same as the last one. I have the same two curves. My cylinders' heights are based off of the same two curves in the same way. My cylinders are way wider. My radii are a lot bigger, but the heights of all my cylinders are the same. X minus x squared. The curve farthest away from the x-axis minus the curve closest to the x-axis. And again, dx. Okay? So we've done rotating around the x-axis, rotating around the y-axis, rotating around a vertical line that's not the y-axis. So let's just do one more example, rotating around a horizontal line that's not the x-axis. Okay? So let's rotate this time. That last one we rotated around x equals 3. This time let's rotate it around just right here, y equals 1. Let's rotate around y equals 1. So it's going to be something like that. If this is 0 and this is 1, this is 2, is where that piece is kind of meeting up right there. So here's kind of our shape here that we're rotating. So if we're going to make cylinders on this thing, they're going to be kind of like this direction on here. Okay. This one, again, because we're rotating around a horizontal axis and we're using these cylindrical shells, I like to just use the side of my shell to kind of think about, okay, yeah, that's super thin in the y direction. It's got some length in the x direction. That's going to be my height. But it's really thin in the y direction. So I know I'm in terms of y here. 2 pi can come out of our integral. Then we need the radius. So the radius here is going to be from our axis to our curve. We have all these different radii all along here. So it's going to be 1 minus y. Y is going from 0 to 1. Our original shape in the y direction went from 0 to 1. So we're doing 1 take away y. Up here is where we're doing 1 take away the 0 part. And then they just get smaller and smaller until we get to 1 take away nothing. So we've got 1 minus y. And then our curve that's farthest away from the y-axis is that x squared, which we solved earlier to be the square root of y when we change it into our other variable. And then the one that's closest to the y-axis is the y equals x, or x equals y when we switch. So this is our radius. This is our height. This is this length from here to here is square root of y, take away y. That gives us this length right here. And then that's also dy. So there's your quick lesson, a little bit faster than the last one, on volumes using cylindrical shells. I will also make a discussion where you guys can ask questions for me and for each other, share any other videos that you found that you like that are helpful on this topic. And again, we'll try and do that live chat on Monday. So try and get onto that if you can, and we'll do some questions there as well. Okay, good luck guys, and have a great weekend.